Hi folks. Today's video is going to walk through the ideal gas law lab in the LabFlow um, laboratory environment. So this lab gives us the opportunity to calculate experimentally the gas law constant. Now you've probably learned in lecture classes and in lab settings that the R value that we talk about for gas laws has a couple of different numerical values depending on the units. The reference one that we'll be trying to emulate or trying to compare here is 0.08206 liter atmospheres per mole Kelvin. Remember, if we had a different pressure unit here, if we were using the torr unit, this would be a different number, somewhere around 62. But in our case, we're going to be using these units of liters and atmospheres over mole Kelvin. So the way that this lab is done is that we do a reaction that produces a gas, and a very sort of common one is this one here, where we use some sort of an active metal, react it with an acid to produce a metal salt that's soluble, and then hydrogen gas. That hydrogen gas is captured using a device called a eudiometer. And basically, as the description here tells us, that gas is captured as it bubbles through water. And so we would direct the gas outlet, the tube coming out of the reaction vessel. We would have a flexible tube that went down here into the eudiometer under the surface of water here. The eudiometer itself is full of water to begin with. And so as that gas is produced, in this one they have the metal inside rather than a tube. The one we have in our physical labs has a tube. The gas is produced, it bubbles up here, it would fill the top of the eudiometer with hydrogen gas, and then it would displace water out into the beaker. The beauty of this thing is that by measuring the pressure in the room, we can determine what the pressure of the hydrogen gas was in the first place, because of course the pressure that's pushing down here, atmospheric pressure, that pressure pushing down on the outside is going to be the same once the reaction is done. It's going to be the same as the pressure of the gas inside that tube. That pressure inside there is a combination, though, of the pressure of hydrogen, which is what we're worried about or what we're trying to figure out, but also the pressure of water vapor. Because the hydrogen is bubbling through water, we need to take that into account. And so we'll get into that in the calculations here in just a little bit. Okay, let me get rid of my little bubbles there, and we'll go forward. So what we're doing here, I'm going to skip the rest of the procedure. What we're doing here is looking at doing that reaction. So as you go through the LabFlow procedure, you will be given some values. You'll be reading the values off of the sample data and collecting those here for one trial and then for a second trial. Now in the lab we might do 3 or 4 trials so that we have better numbers when we average them at the end. You're only being asked to do 2. So just by way of some sample data here, okay, if I were to read that in LabFlow, maybe I'm given something like 0.035 grams of magnesium ribbon, okay? It's going to show me a thermometer. Maybe I measure the temperature in the room, 22.1 degrees Celsius. I read the eudiometer, and I'm going to read something like 30.52 milliliters. Now, you want to be careful with the eudiometer, because if I draw a little excerpt of it here, it will be numbered sort of backwards. Remember, this tube is upside down in that beaker of water, way down at the bottom. So you want to make sure you're reading it the right way. If I had 30.52, it would be the value would be somewhere in here, okay, full of water like this. So make sure you're reading it correctly as far as reading it up or down. Okay. Um, Atmospheric pressure, you're going to be just given that number. So you'll read that. I'm going to put in a sample value here, 754. The number you're given is in the torr unit. Historically, we would have called that millimeters of mercury. It's the same thing, but more modern versions use the unit of torr. Now this is the total pressure. Like I mentioned, this is atmospheric pressure, which is equal to the pressure of the gas we care about and the water vapor. And so we need to know how much that water vapor contributes. It's going to be just a little bit, but we have to know what this is. Now, where do we get it? For that, we're going to go to our reference book. And in the lab, we have this gigantic book called the CRC Handbook of Chemistry and Physics. Gigantic, real thin-paged, small print kind of thing. It's, of course, digitized as well. And you can look up the vapor pressure of water at all kinds of temperatures out to, 9 decimal places or something. In the case of this lab, we're just going to go up and, pardon the scrolling, just use their table. Okay, pick the temperature value that's closest to what you're doing. And so I think I put 22 down there. We'll double check in a second. 19.8 torr would be the value I'd be going for. Okay. Good, I did. Yeah, so 19.8 torr is what we're going to put in here. All right. Sorry for the handwriting. Torr. Great. Okay, so that's my data collection. Now you will go through and do it again for trial 2. I'm not going to do that in this example, but you'll do another set of measurements. They'll be similar, but somewhat different. Okay. Now, data analysis. Note these units. In order to get the units that we want on our R value, and that is liter atmospheres per mole Kelvin, we need our volume in liters. We measured it in milliliters right here. So of course we just divide by 1,000. So my 30.52 up there becomes 0.3052 liters. Okay, just to divide by 1,000 from what we had up above. Temperature here is just a conversion. We measured temperature in Celsius. We need temperature in Kelvin, and the conversion for that says to add 273.15. So 22.1 plus 273.15 gives us 295 and a quarter. All right, 295 and a quarter Kelvin. Okay, always Kelvin for temperatures when we're talking about gas laws. Moles of hydrogen gas now is a little bit more complicated. We need to do a little bit of stoichiometry. So up above at the very, very top of this thing, I'll save you the scrolling. Up above, it showed us that the reaction was magnesium plus HCl to make magnesium chloride and hydrogen gas. And of course, we have to balance that. We just have to put a 2 right there, and then we're balanced. Notice here that if I know the moles of magnesium that I put in, I can easily calculate, in fact, they'll be the same number, moles of hydrogen gas. So I'm going to do that. I was given 0.035 grams of magnesium, so 0.035 grams of magnesium. Little stoichiometry problem. I'm going to go to my handy periodic table and remember that it's 24.3 grams of magnesium for every mole of that stuff, mole of magnesium. And then I'm going to write this just for the sake of writing that our reaction is a 1 mole to 1 mole ratio. Okay. If you weren't using this particular acid, maybe this would be a different ratio. All right. So in our case, let's pull up our math. We're going to go 0.035 grams divided by 24.3, or maybe you want to do 0.31, be a little bit more precise there. Now we get an itty bitty number. Okay. I'm going to see if I can make this stay put. There we go. Great. We get an itty bitty number there. I want to save some of that precision. All right. We're doing we're going to end up with a very small result, 0.08 something. It's a small number. And so I don't want to round this really. So yes, by significant figures, I should stop at 2, but this isn't a final answer, right? So 0014, maybe I'll just keep a few more decimal places, okay? And this is moles of hydrogen, all right? So moles of hydrogen gas, 0.0014397 moles. Look, if you want to keep 20 decimal places, great, do it. But our answer, our final answer, will be something like 4 significant figures, right? Our reference value is 0.08206. So, you know, that would be here. So if I keep an extra digit or 2 even, I'll be in good shape. All right, pressure of the gas, just hydrogen now. So I'm going to use this little equation that I referenced earlier, right? I know my atmospheric pressure was 754 torr. I'm not sure of this, and my water pressure was 19.8. And so when I subtract those, 754 minus 19.8 is going to give me 734.2. Now, most common wrong answer that I just wrote down here, because watch those units. What I've done here is torr, which is fine, but to get to atmospheres, I then have to divide by 760. Okay, that's just a conversion from torr to atmospheres. So I'm going to take my number, divide by 760. Now again, cross this out because we both know now we don't want torr. And again, I'm going to keep some of these decimal places. Okay, so 966. I don't know what, 053 maybe. Okay, proper, the most precise answer would involve keeping everything, right? Keep everything your calculator gives you. However, when I'm writing it down, we often don't want to do that. So if you're going to shorten it, save a couple extra decimal places beyond where you will eventually round. All right. Now, experimental value of R. Don't just put in the literature value here, okay? We're trying to determine the value, so we can't just put in the literature value. I'm going to start with my ideal gas law, PV equals nRT, right? You can plug and chug, or you can rearrange to say R then is PV over NT, and use these numbers. All right, pressure, 0.966053 atmospheres. Volume in liters, 0.03052 liters. Divide, great big divide line. Moles, 0.01437. And temperature, always in Kelvin for gases, 295 and a quarter. Okay, all right. I don't know what I just did there. Let's cancel that out. Okay, great. So when I do my division now, all right, calculator, don't fail me now, 9666053 times 0.03052. Divide by 0.01437 and divide by 295 and a quarter. I should get an answer that's at least on the same scale as the literature value, right? 0.0 something. 0.082 is the the literature value. Mine's 0.069, pretty terrible. But oops, I made up these numbers, so maybe not so bad. 0.696 right? Liter, atmosphere, mole, Kelvin. Now this is the number that I would round off because this is my final answer, okay? So I'm going to go all the way back here and I'm going to say, what do I need to round off? Well, my temperature has a bunch of significant figures. Here, all of these were calculated data. What did I actually measure? Way back up here, I only had 2 significant figures in my magnesium mass value, the way that I wrote it down here. And that's what the balance looked like in my version of LabFlow. Now, if we had used a better balance, we could have gotten 3 or 4 decimal places maybe, but this is what we had. 2 significant figures right here. It's our least precise number, and so that's where we would have to round here. So round to 2 significant figures, I would report 0.070. All right. You're going to do it twice through, 2 trials. Get that out of the way, 2 trials, and then you're going to average those 2 trials, right? Add them together, divide by 2, no big deal. And then percent error. Remember, percent error is always the difference between your value and the accepted value, or the right answer, if you know it. LabFlow tells you specifically the value to use there. Okay, so that's written in there, 0.08206. So you'll do percent error, the difference divided by the accepted value times 100. You can see mine, not great, but yours probably will be much better. All right, so that's how we do this kind of a lab. I hope that makes sense. If it doesn't, obviously, please reach out to me and I am happy to help. So with that, have a great day, keep up the great work, and I'll talk to you next time.